Hello everybody and welcome back to our video lectures about parallel programming and general purpose GPU programming. In this class, now that we have looked at some fundamentals of parallel programming and parallel communication patterns, just an overview, it's the time that we would get to know our hardware a little bit more. So in this unit, I'm going to go over the general PC architecture very briefly, and then look at the relationship and the communications between your PC and the graphics processing units that we will be discussing. And then we'll look at the architecture of the GPUs in general, and then in particular the architecture of the NVIDIA graphics cards that have embedded CUDA architecture. We'll see what makes them unique and quite useful. In fact, a supercomputer within your desktop. And then we'll look at the compute levels of these architectures before we go into the programming aspects of this class. This is just a generic overview of your PC, essentially Intel-based computers. What you have, in fact, are two different kinds of bus systems that connect your processing units, that is your central processing unit and your graphics processing units, with each other, and also connect those with your storage units. And you have two different kinds of storage units. You've got your primary storage unit as a dynamic RAM, and then you've got your secondary, so the RAM is your primary storage unit, and then you've got your secondary storage units, which could be in the form of your hard drive, your solid state drives, your USB drives, your optical drives, and so forth. So you have some data and address buses that connect your memory to your CPU, either secondary or primary memory units, and then you've got the a bus system that communicates between your graphics processing unit and your central processing unit. So this is the overview architecture, and we'll go into some details about what has changed as far as the Intel architecture is concerned, as well as the AMD, and what are the benefits and drawbacks of each. One of the things to notice is that the primary communication pattern, primary communication bus that connects your CPU with the rest of the world is through your front side bus system. And so that is the primary highway connecting your processing units. Also notice that your graphics processing unit, especially the high throughput units, are connected to your processor through what is called a PCIe bus. And generally speaking, before PCIe 3, essentially PCIe 2 was very much in use, and nowadays the PCIe 3 has been introduced, and now the motherboards basically come equipped with a bunch of PCIe 3 connections. PCIe 2 specifications were essentially at the transfer rate of about 5 gigabits per second, and PCIe 3 significantly changes that communication speed. The PCIe is your Peripheral Communications Interconnect Express. It's essentially the expansion that occurred over the general industrial grade PCI, and the PCIe is an interesting bus because it's based on guaranteed bandwidth. What that means is that in the case of your old PCI systems, you could use the full bandwidth of the bus but only one device at a time could connect and work with the full bandwidth. So if the more cards you added to your system, the lower it would have been the amount of, or the bandwidth or the speed at which each card would be able to communicate its data between between the processing unit and its own unit. PCIe solved these problems by introducing PCIe lanes. These lanes are high-speed serial links that you can combine them together, or can be combined together, in 1, 2, 4, 8, and 16 lines. And that's what you see usually next to a PCIe specifications. You see a like X16 that specifies that it has actually 16 parallel lines connected. Most GPUs use at least PCIe 2 with the 16X specifications. And with this setup, you will have a 5 gigabit connection, full duplex bus, and that connects your graphics card with your central processing unit, and you get the same upload and download speeds at the same time. So with this specification, you can transfer up to 5 gigabits per second to the card, while at the same time you can also receive 5 gigabits per second on the card. So generally speaking, in both directions, you get upwards of 10 gigabits per second transfer rate. The problem, though, is, remember, this is not really 10 gigabits per second in one direction. It's basically you're not receiving the data at 10 gigabits per second. It's basically you can send from your card to your CPU at 5 gigabits per second, and you can receive at 5 gigabits per second. So this is not shared. This 5 gigabits per second is not shared in the two receive and send direction. One of the things that you need to notice as far as the problem with for example, a Core 2 layout of your interconnects is that it would allow you to use a PCIe bus, and again here this graph basically assumes a 2.0 x16 bus specifications at 5 gigabits per second, and so you can plug your graphics processing units over the PCIe bus, and you can have like 8 of these graphics cards, and then you can also have your RAID drives that would be SATA at 300 megabits per second. You may connect your Ethernet connection at 10, 100, or 1000 bits per second, and then you also have your DRAM units. The problem is that with the Core 2 layout, all these units were essentially connected to your PC through your North bridge, except that your secondary storage units, such as your Ethernet and your SATA connections, would go over your South bridge, and your RAM and PCIe Express bus would connect through the North bridge. But this connection would have to happen over your front side bus. And the problem with the front side bus is that it can run up to 1600 megahertz clock. So the front side bus clock rate is limited to, so the clock rate here is limited to about 1.6 gigabits per second, and that would be essentially the limiting factor in terms of Core 2 layout, in that the front side, the PCIe Express is capable of 5 gigabytes per second, but it goes through your front side bus, and that usually is designed at much lower rates of the speed of your processor, let alone the speed of your graphics PCIe Express. In a typical supercomputing environment, or even in your desktop application, we're basically dealing with a large data set. Usually you deal with petabytes of data, and we need to be able to handle this. And even in a desktop application, if you have a computer game application, you usually are dealing with several gigabytes of high definition video, and in both cases we need to be able to fetch the data as fast as possible from your attached peripherals, and to be able to communicate this data with your your processing units. So as I showed you, the PCIe Express essentially attempts to solve this problem, or rather the bandwidth of your communication between your graphics unit and your central processing unit over the high speed PCI Express lanes. And this is a major, or rather starting with the Core 2 application and the introduction of PCIe, was a major advancement in terms of data communication. CUDA allows us to use GPU direct technology, which which became available after the CUDA 4.0 SDK, and with this direct technology, we will be able to actually communicate and talk directly to the GPU without having to go through our CPU first. I'm not quite sure if we get to these topics, but if you're inclined to look more into the hardware details of your application and your CUDA, you might want to look at this area and see how you can how this can be used. But all in all, if you look at your GPU CPU communications bus connecting your GPUs and your CPUs, all of your GPUs are connected through your high-speed PCIe bus that is quite fast and high throughput, and your CPU is connected with the rest of the peripherals through your front side bus, which is usually an order of magnitude slower than the speed of your CPU. So PCIe is essentially not, or rather, the communication speed between your graphics card to CPU is not really the limiting factor in terms of your speed and throughput of your data communications. The front side bus is the bottleneck. So direct technology tries to solve this problem. If you had a multi-GPU application and you wanted the graphics processing units to communicate the data between each other, they don't have to really necessarily go through the CPU to directly communicate with each other. So SLI technology and the direct technology are available to help with this problem. Everything else, as far as your primary units, are connected to your CPU through the north bridge, and then slower components such as your hard disk drive, USB, and others are connected to your south bridge. There's possible, if you have a high-speed solid state drive, that you needed it to communicate at a faster speed than is accessible and available from front side bus, or rather the south bridge. It's possible to connect your SSD drives to your PCI Express, although it's not really that much use, specifically if you have high throughput applications such as graphic processing and supercomputing. You need to utilize higher bandwidths with it. It's generally preferable. The next architecture that Intel developed brought a number of major changes. And the architecture is the Nehalem X58 architecture and the layout. So as you see here, there were a couple of changes that were really a huge paradigm shift in the architecture, and that is that north and the south bridge chipsets were replaced by the X58 chipset, or rather Nehalem, and basically the new bus that would connect your input-output peripherals to your CPU cores is now the new Quick Path Interconnect, or the QPI bus system. It's actually a huge advance over the front side bus, because the speeds of the communication with the QPI is now at the rates of 25 gigabytes per second, which is a huge improvement in terms of the bandwidth connecting your CPU with your other devices. So basically, the QPI is an incredibly high speed bus, and it solves the problem of the bottleneck from becoming your front side bus or your CPU capability of handling the incoming or outgoing data rates to it, rather than your peripheral connects such as your PCI Express or South or North Bridge connection. So essentially, in a nutshell, you've got your X58 and your 1366 processor socket that can handle up to 36 PCIe lanes available. That means that you can essentially connect up to 2 graphics cards at X16 or 4 graphics cards at 8 lanes, and this way you'll be able to handle a large amount of data transfers. You also have with the Nehalem architecture QPI, Quick Path Interface, that is much faster than front side bus. It's a very, very high speed communication bandwidth, and you can actually run at 4.8 gigabits per second or 6.4 gigabits per second of transfer speeds between your Extreme or Xeon processor versions, depending on which processor, which CPU you have and you're working with. The other major advancement that Intel had put out is the Sandy Bridge design, and in the Sandy Bridge you're basically looking at the introduction of AVX or advanced vector extensions. So generally now the PCI in the Sandy Bridge connection is directly connected to your Sandy Bridge chipset that connects to your central processing unit at your 10 gigabits per second, or rather 5 gigabits per second half duplex speed. You've got your DRAM that can be now connected at 18 gigabits per second with your CPU, and your peripherals are using the DMI access that connects your I/O hub at 20 gigabits per second with your CPU. So what Sandy Bridge brought is support for SATA 3, and that is 600 megabit per second I/O interface connecting your I/O units directly, which is a serial bus. You have the support for advanced vector extensions, and this allows you to. It's also supported by AMD processor, and it allows for vector instructions that can be essentially useful for up to about 4 double precision vector operations. And that is 256 bytes or 256 bits or 32 byte operations, and essentially this is in essence bringing in per instruction more data in one clock cycle. So as you can see, that's the advantage in double precision speed that you get when you look at computational bounds on your CPU. The only downside of Sandy Bridge design is that it only supports 16 PCIe lanes, and essentially that is limiting because it theoretically limits the bandwidth of your PCI Express bus to a theoretical limit of 16 gigabytes per second, but rather at about an actual 10 gigabytes per second bandwidth. With this limitation, you basically can think that if you're using a graphics processing card and it needs 16 lanes, essentially all you can handle is only one graphics card. Now, how does this compare with the AMD design? So AMD still connects your PCI Express bus to the North Bridge. Your secondary storage units, your RAID drives, your SATA drives are all connected through the South Bridge. The North Bridge connection to your core CPUs are at 25 gigabits per second, and your DRAM is connected at 17 gigabits per second. The FX chipset of the AMD architecture can provide either 2 16-lane devices on your PCI Express bus or up to 4 8-lane PCI Express connections. So basically the AMD connections are a little bit more consistent in terms of the number of lanes that are supported on PCI Express connections, and also that they would give you a little bit more number of graphic processing unit connections than Sandy Bridge did. The only major difference between AMD and Intel is the price point. AMD's are cheaper at a lower price point compared to your Intel counterpart. Generally, with the same price, you get more cores on the CPU devices, but the downside of AMD is the support for dual channel memory, which is basically a significant drop in the bandwidth between your RAM and your central processing unit. So if you really are contemplating about connecting more GPUs with more cores available, you would go with the AMD. Otherwise, and of course the price wise, otherwise you'd be probably better off going with an Intel design as far as the speed and the throughput of your data communication is concerned. Now that we've looked at the architecture on the CPU side of GPU CPU communication and programming, let's take a look at graphics processing units architecture. GPU hardware is radically different than the CPU hardware. As shown in this picture, on the other side of the PCIe bus, notice that the GPU hardware basically is composed of a number of significant key blocks. There's essentially your memory units, and the memory unit comes in several forms. You would get your global memory. Essentially, it's an incredibly fast and a very large memory unit that through your global memory bus communicates with both your CPU through the PCI Express bus and to your processing units on the GPU, which we'll talk about. You also have another kind of memory that's basically shared between subcomponents of your processors within your graphics processing unit. It's called constant and shared memory. And you also have a constant memory unit, which can be in the form of a view of global memory copied into the register banks of your processing units in your GPU, or the texture memory. The next component is a bank of what we call symmetrical streaming multiprocessors. So, and here's, for example, in this particular case, you've got like 4 streaming multiprocessors. And if you look at each of these streaming multiprocessors, they are broken down in smaller processing units, which are basically are also called simple processors or streaming processors. The main thing that you notice here is that GPU is really an array of streaming multiprocessors, and each of those streaming multiprocessors come with a set of N cores, which we refer to them as the simpler processors, and any GPU that you look at, they come with equipped with one or more of these streaming multiprocessors. This is the core of or the basis of the scaling of your graphics processing unit. This is this multiple number of streaming multiprocessors and the architecture that governs them is what makes the graphic processing devices or the GPU devices basically scalable to the tasks. If you add more streaming multiprocessors, and if your task has enough parallelism associated with it, you can scale up and speed up the process drastically. One of the things to notice, and we'll go over this a little bit later in the semester, is that the parallelism that can be exploited from your GPU is completely handled on the GPU side. The GPU decides which task and which thread and which units will be associated to which streaming multiprocessor, and that is not something that the programmer has control over. It's completely done on the hardware side. It has down and up sides. The downside of it is that you cannot specify tasks that you want them to run together, because you don't have control over them. And the upside of this is that your GPU scheduling and hardware architecture will take care of task association and optimization of your tasks on the GPU. If you look at a CPU parallelism, when you have a dual core CPU and you have written a software that works and is designed to run on the two cores, when you double the number of cores and you come up with a quad core, the user sees no benefit. So you would have to redesign and rewrite your software to essentially make use of the additional cores that are available. This is almost true to some extent, and in terms of software development and programming side of it, we get into it a little bit later in the semester, on the GPU programming and design as well. The difference between the streaming multiprocessor scalability of your graphics processing unit with the number of cores on your CPU is that since the task association of your software that runs on your GPU is done on the hardware level, as long as you have enough parallelism developed and associated within your program, you will be able to easily, or rather more easily, scale up your application when you have more streaming multiprocessors, or the properties and specifications of your streaming multiprocessors change on the GPU side. You'll be able to, you still need to modify the software if needed, but you'll be able to exploit the aspects of parallelization on your graphics processing unit easier in your graphics graphics processing application. Now let's take a look at a streaming multiprocessor itself. In the previous slide, you saw that the GPU is composed of a global memory unit and other additional kinds of memory, and banks of streaming multiprocessors. Within each, there are simpler processors. If you look at one of these streaming multiprocessors, you would see that there are a number of key components that make up each of these streaming multiprocessors. The most significant part of streaming multiprocessor components are multiple simpler processor units, and we denote these as the SP units in this graph. So for example, in this case we are showing 8 of these SP units. Fermi architecture has 32 to 48 simple processing units, and Kepler's have 192 SPs. Each of these streaming multiprocessors will have access to a register banks, or rather the register files, which is much like a chunk of memory that runs at the same speed as your SP unit. So effectively there's zero wait time and latency associated with this unit. The size of this memory varies from generation to generation of your GPUs, and it's used for storing register values and basic local variable association and values within each thread that is running on your simple processing units, or your SP. You also have the shared memory bank, which essentially is a local copy, a local kind of cache system on chip within each of these streaming multiprocessors. And the threads that will be running on as a part of a block that's associated to that streaming multiprocessor will be able to associate and access this shared memory. and it is handled and done pretty much like as a program managed cache. And we will see how you can declare and utilize this shared memory, and what are the advantages of using shared memory, namely the speed, and what are the pitfalls, and essentially what are the things that that as on the programming side we should be extremely aware of when we are utilizing the shared memory. Unlike CPU cache, there's no hardware evicting cache data behind your back when you are programming on streaming multiprocessors. It's entirely under the programmer's control about how you would like to allocate these memory units, how you would like to use them, and so forth. And this is one of the things that later on, when we talk about optimizing your parallel programs in CUDA, we will talk about what makes it, how this control on the programming side is good to have, and how you can actually utilize this control to your benefit in terms of optimizing and speeding up your application. Each of these streaming multiprocessors also have a bus that connects them to texture, constant memory, and their L1 cache, and also how you would be able to connect to the global memory. Notice that the constant and texture memory, and we'll talk about these again later on in the programming components of this class, that they are faster memory units because they are highly specialized memory units that are accessible and available to each of these streaming multiprocessors, and they are essentially can be utilized as a view, a look into the global memory. So that's another way that you can communicate data between your threads and blocks through texture memory and constant memory with within and between streaming multiprocessors. So again, to go over what we have in terms of our GPU hardware architecture, it's radically different than the architecture of the CPU. There are 4 basic components to your GPU architecture. You have the memory units, which are high-speed units of primary memory accessible to your graphics processing unit behind the PCI Express bus, which makes it faster to process and run applications on the graphics card. There's no need for communication outside of the card if there's no need for such communication. These memory units are in the form of global shared constant and texture memory. Global memory is a memory that is available to all streaming multiprocessors, which is the next big component of your graphics processing units. And so any thread block running on the streaming multiprocessor, any streaming multiprocessor will have access to it, to the global memory. Within each of the streaming multiprocessors, there's a bank of shared memory unit in which the threads within a block on that streaming multiprocessor will have access to. And then you'll have also constant and texture memory. We'll talk about this in the next slide. As I said, the next big component of your graphics processing unit is streaming multiprocessors, and it's basically they act as cores on your GPU, just like cores on the CPU. They're completely independent processing units, and you can have up to 48 or 192 in Fermi and Kepler architectures. And then within each of these streaming multiprocessors, you have a simpler processors, and these simple processors are essentially blocks of processing units that have access to shared register files, and they are the basic components on which your threads will execute. As far as your memory access, the global memory is shared between all of the streaming multiprocessors. So all your inter block and inter-processor communication happens over the shared memory. It's a slower memory, although it's on the GPU, but still it's the slowest kind of memory available, and it's also the pathway to your CPU. And in the next unit, when we talk about writing CUDA programs, we'll see how we can communicate data between the DDR RAM on the CPU side via the PCIe Express to your GPU DDR5 or DDR3 global memory. Then you have shared memory, which is shared between all the streaming processors or simple processors within each of the streaming multiprocessors, and it's basically used primarily for thread communications in thread blocks. You have constant and texture memory, and constant memory, of course, as the name says, it's a constant read-only memory, and it can be used as a faster version of accessing and viewing the data in the global memory. You cannot change the value of this data though. And the texture memory is an ultra-efficient memory that is specifically designed for pattern data. If you have a data that is naturally in the two-dimensional or three-dimensional pattern, like for example processing images and things like that, you will be able to utilize texture memory to get more efficient and faster processing as a part of data access. Now, on the computational side, CUDA supports a number of compute levels. And starting with the original G80 series graphics cards that was shipped with the first version of CUDA, the compute capabilities is essentially fixed into a hardware. And if you wanted to upgrade to a newer compute capability, you would have to upgrade your hardware and get a newer version of the graphics cards with the new architecture and compute level embedded inside of it. If you go on the CUDA capable GPU link on CUDA developer website, you would see that next to each of the graphics cards there's a number, and that number is the compute level integrated within the hardware on that graphics cards. The compute levels are categorized into the major revision and the minor revision. So the number before the period in the compute level is your major revision, and the number after is your minor revisions. And there are three categories, three generations so far, three major revisions: compute 1, 2, and 3. Compute 1 comes with compute 1.0, 2, 1, 2, 3, 4 different major revisions. Compute 2, we talk about 2.0, 2.1, and 2.2. And the latest revision that has just been released is the Compute 3.0 level. Compute 1 major revision is found on the oldest graphics cards capable of CUDA. And for example, the original 8800 Ultras and many of the 8000 series cards and the Tesla C, D, and S come capable with this revision. The main features that's basically lacking in Compute 1.0 cards was the lack of atomic operations. Atomic operations are those operations that you can guarantee a completion of that operations without thread interruptions and thread interferences. And we'll see an example of this later on when we will discuss the shared memory. And the example we will discuss is the example of calculating histograms. When you have multiple threads competing for access to a shared memory location, in order for ensuring the completion of each memory calculation within each thread without the interference with from other threads, we would have to lock the memory access to a location, and atomic operations ensure that operation. They can be done in the form of adds, subtractions, min, max, and logical and, or, XOR, and so forth operations. Compute 1.0 are effectively obsolete now, and we'll just basically talking about them now. The next revision is Compute Level 1.1 that is found on 9000 series cards, and it was extremely popular back then. They were based on G92 hardware as opposed to the Compute 1.0 devices that were based on G80 hardware devices. One major change that was designed within Compute 1.1 device was support for overlap data transfers and kernel executions. If you use the CUDA get device properties function call in the CUDA SDK, which we'll see later on, one of the return values is the device overlap property, which defines if this functionality is available. This allows for optimizations that can be done. It's basically called double buffering, which works as shown in this picture. So you have your processing, or rather the cycles of an execution cycle split into several cycles. Here, for example, say cycle 1, 2, and so forth. And you have two buffers that are available to your GPU. So in cycle 0, when the GPU idles, then your CPU fills the buffer 0 with the data that needs to be transferred to the GPU. And in cycle 1, GPU will be able to work on buffer 0 and process the data on process buffer 0 while your CPU at the bottom of this image will be transferring data into buffer 1. And then in the next cycle, your GPU can move on to process buffer 1, and then the CPU will be able to read the data that was created by the GPU and put in buffer 0, and at the same time fill buffer 0 for your GPU to process next. And then the CPU and GPU basically will be able to flip-flop between the two double buffers that you have here, and this effectively doubles up the speed of your processing. So this is essentially a means for a CPU to GPU and GPU to CPU transferred over your 5 gigabytes per second PCI Express bus. And this dual buffering extends and basically largely hides the latency that the CPU and GPU will essentially be subject to if you didn't have a dual buffering mechanism, which Compute 1.1 supports. Compute 1.2 devices appeared with the GT200 series hardware, and the initial Compute 1.2 devices were 260 and 280 cards. NVIDIA essentially approximately doubled the number of CUDA core processors on these cards by doubling the number of multiprocessors present on the cards. In effect, this doubled the performance that could be exploited from the previous versions of your compute level. Also, there was an increase in the number of concurrent warps that a multiprocessor could execute. Used to be 24, and they increased that number to 32. We'll talk about warps later. They're blocks of code that can execute within a multiprocessor, and increasing the amount of warps per multiprocessor gives you more scope and better performance in terms of the scalability of your application. Also, there were issues with coalesced access to the global memory and bank conflicts with the shared memory that were from Compute 1.0 and 1.1 devices. They were greatly reduced, and the performance of these devices were essentially quite superior. Compute 1.3 devices were again with the future revisions on the 200 devices. And the major change that occurred with Compute 3 hardware was the introduction of the support for limited double precision calculations. Primarily, GPUs were used and aimed at graphics, and therefore there was a huge need for fast single precision calculations. But this limit basically poses a huge restriction on the double precision capabilities of your cards. If you were to perform a double precision calculation, you'd see an order of magnitude drop in the performance as opposed to running single precision floating point operations on the GPU. With this access to double precision introduced in Compute 1.3, that limitation was addressed at least at least slightly. The next major revision to the compute level, which was introduced after the switch to the Fermi hardware, was Compute 2.0. The original changes that were introduced with Compute 2 hardware are basically the introduction of 16 to 48 kilobytes of L1 cache memory on each of the simple process units, introduction of the shared L2 cache for all of your streaming multiprocessors, the support in Tesla-based devices for ECC or error correction code based memory checking and error correction, the support of dual copy engines, the extension in size of the shared memory from 16 kilobytes per simple streaming multiprocessors to 48 kilobytes per streaming multiprocessors, the optimization of coalescing of data, that it needs to be 128 byte aligned, and the number of shared memory banks that was increased from 16 to 32 for streaming multiprocessor, or rather simple processors. So let's take a look at some of the implications of the changes. Let's first look at L1 cache. Compute 1 did not have any cache, but the Compute 2 architectures started supporting a level 1 cache on each of your simple processing units. This makes it easier for many programmers to write the programs that work really well on the GPU hardware. It also allows for applications that do not follow a known memory pattern at compile time to be able to essentially exploit the cache information and the cache accesses. If you have the two forms of temporal and spatial locality within the memory accesses in your data. Also, you've got your L2 cache that is basically a unified cache, and it is shared and provides consistent access and consistent view for all of your streaming multiprocessors. And again, this will be hugely important, because as programmer, you have no access to how your thread blocks are going to be allocated and assigned to streaming multiprocessors. So that uniformity within the data access will help and make for some optimizations on that line as well. So this, in effect, allows for much faster interblock communication through your global atomic operations. Dual copy engines that was also introduced in Compute 2.0 allows us to extend the dual buffer example from Compute 1 that we saw earlier to multiple streams of processing. So basically, you can think of n independent kernels to be executed in a pipeline fashion. So for example, once stream 1 is basically copying the data to the device, then running its kernels, then stream 2 will be able to copy its data to the device. And then while stream 0, the top stream, so you would have your stream 0 copy data to the device, and then while the kernel of stream 0 is being run over here, stream 1 can write its data to the device. And while the kernel for stream 1 will be running, then stream 0 could take its data off of the device, and then stream 2 will be able to run or copy its data into the device. Next, while stream 2 is basically executing its kernel, stream 0 can write the data, and stream 1 can pick up its data ready to be read from the device. So these streaming engines essentially creates or rather dual copy engines would allow for even better pipeline processing architecture on your dual buffering. And finally, we'll talk about Compute 2.0, or rather Compute 2.1, and see the changes in this level. It's seen on certain devices aimed specifically at gaming market, such as the low-end GTX 460s and GTX 500 series. These devices essentially change the architecture by using 48 CUDA cores per streaming multiprocessor instead of the usual 32 per streaming multiprocessor of the Compute 2.0. There were 8 single precision special function units that can be used instead of the usual 4, and then you have dual warp dispatcher instead of the usual single warp dispatcher in the units. One of the important points to notice on the Compute 2.1 hardware is the sacrifice of the dual precision hardware to increase the number of CUDA cores. Since these devices were specifically targeting the gaming market, they really didn't need that much of the need for the support of dual precision hardware. So if you have single precision and integer calculation dominated kernels, this is a very, very good trade-off, because you get a huge amount of scale-up in your processing by introducing the larger number of CUDA cores onto your units, and if your calculation does not need dual precision floating point data operations. The number of warps also, or the dispatching of the warps, were also doubled. And essentially warps are groups of threads, and we'll talk about these a little bit later. On Compute 2.0 hardware, we had a single warp dispatcher. It takes 2 clock cycles to dispatch instructions to an entire warp. On Compute 2.1 hardware, instead of the usual 2 instruction dispatchers per 2 clock cycles, we now have 4. In the hardware, there are 3 banks of 16 CUDA cores, basically 48 CUDA cores in total, instead of the usual 2 banks of 16 CUDA cores. The Compute 2.1 is actually a superscalar approach. It's similar to what is found on the CPUs from the Pentium CPU and so forth. To make use of all of the cores on the hardware architecture, the hardware needs to identify instruction level parallelism within a single thread. This is a significant divergence from the universal thread level parallelism approach that was seen in the previous architectures. The performance of 2.1 compute hardware varies. Some of the well-known applications, such as folding at home project, that is a gene folding, or rather protein folding graphical application designed and implemented in Stanford, performs really, really well with 2.1 hardware. Other applications, such as video encoding, in which it's much harder to extract instruction level parallelism, and the memory bandwidth is a key factor, typically perform worse. So basically, if you have applications that are essentially have universal thread level parallelism, or require memory bandwidth, or floating point calculations, tend to perform better on 2.0 architecture or Compute 2.0 level. And the applications that you have instruction level parallelism within a single thread, and also are heavily single precision integer calculation operations, they tend to perform better if you go with a 2.1 architecture. There's 3.0 platform that has just recently been released, and we will not cover it since they are relatively expensive cards, and they're quite new actually to the market. So this finishes our overview of the CUDA hardware architecture and the GPU CPU communication patterns and hardware platforms that is at our disposal. I'll close up this unit and the discussion of our hardware, and from this point on we will go into implementing and starting to write our programs in CUDA. What I would like to know is if everybody was capable of getting access to a CUDA capable hardware platform, whether by installing an NVIDIA CUDA capable graphics cards on your desktop, or securing your access to the computer labs at the Sugarland campus or in the Victoria campus. I'll also include within this lecture unit the installation of CUDA SDK and OpenCV SDKs for our programming. So you will have the videos of these two units, which we covered earlier in the semester, first week of the semester, and now we're going to go over those again. And then we will start next in the next unit talking about the CUDA and what it is that we are looking for when we are programming in parallel, and specifically the performance measures that we'll be interested in evaluating our algorithms and our applications by. With this, I hope that you enjoyed this lecture video, and I hope that you enjoy the rest of this class. Thank you and bye.